Today's question is a word problem about optimization in calculus. An offshore well is located in the ocean at a point W, which is 6 miles from the closest shore point A, on a straight shoreline. The oil is to be piped to a shore point B, that is 8 miles from A, by piping it on a straight line underwater from W to some shore point P between A and B, and then on to B via a pipe along the shoreline. If the cost of laying pipe is $100,000 per mile underwater and $75,000 per mile over land, how far from A should the point P be located to minimize the cost of laying the pipe? What will the cost be? This is one of the very common optimization questions you can see in your calculus courses. You are asked to design a most economical pipeline route which conveys oil from the offshore well to a refinery company which is located on the shoreline. Now I'm going to draw the diagram based on the question. This is the offshore well in the ocean, and this is the shoreline. Point A is the shortest position on the shoreline from the well W, and the distance between the well and point A is 6 miles. Point B is a refinery on the shoreline. It is 8 miles from point A, so the pipeline has to be laid partly underwater and partly overland. But their prices are different. Underwater part is more expensive. It is $100,000 per mile, while overland part is $75,000 per mile. How should the pipeline go to minimize the total cost? If it directly go from W to A and to B, the underwater part is the shortest, but the total length of pipeline is the longest. The overall cost may not be the lowest. If we simply connect W and B, we can get the shortest length of pipeline, but it has the longest underwater pipeline which is more expensive than overland. So we have to consider a compromise solution and find a point P between A and B. First, we have to find out the length expression of WP. Look at the triangle WAP. If we let AP be x, and we already know that WA is 6, then by using Pythagorean theorem, we can get the length expression of WP as square root of x squared plus 6 squared. And the length of PB is 8 minus x. We know that the total cost is equal to unit price times total quantity. Here the total cost equals unit price times length. So we can easily find the cost function C in terms of x. It is equal to 100,000, which is the unit price underwater, times square root of x squared plus 36, which is length between W and P. Then plus 75,000, which is the unit price of pipeline over land, times the overland length, 8 minus x. This is the cost function in terms of x. Next, we are going to take the first derivative of this function to find its critical point. It is a composite function, so we have to use the chain rule to differentiate it. Just a reminder that the derivative of a composite function equals the derivative of its outside function, and then multiplied by the derivative of its inside function. Taking the derivative and simplifying, we can get 100,000 x over square root of x squared plus 36 minus 75,000. Let it equal 0, and then solve for x. Move 75,000 to the other side of the equation. Now isolate square root of x squared plus 36. This is a radical equation. We know that in order to get rid of the radical, we can square them on both sides of the equation. After squaring them, we now get 16x squared over 9 equals x squared plus 36. Multiply both sides by 9. Now we get 16x squared equals 9x squared plus 324. It is easy to figure out the value of x. X equals square root of 324 over 7, so the x value is 6.803. This is the optimal distance from point A, which makes the total cost minimal. To find out the optimal cost, we simply plug in this x value to the cost function. Just replace x with 6.803, then we can get the cost value. It is $996,862.70. So if we lay pipes in this route, the total cost will be a minimum